We now go to the next presentation by Gary Cheng. Gary Cheng is the FCC Regional Marketing Manager for Grace and is based in Singapore. He has more than 13 years of industry experience. He has spent most of his career at Grace in North America as an FCC technical service and sales manager before relocating to Singapore. Prior to Grace, he was employed at ExxonMobil and has held various roles in the engineering office and refinery operations. Over to you, Gary.
Of the GRPC conference for allowing us to present at this prestigious event, and certainly want to thank all of you for your time and attention during today's talk. As mentioned, my name is Gary Chang, and I'm proud to be up here representing Grace and talking to you about high rare earth FCC catalyst technologies for maximum refining profitability. To start off with, a little background about Grace and also a fun fact, actually. This coming Monday marks the 80th anniversary of the first commercial production of synthetic FCC catalyst, which was done by Grace. And towards the end of this month marks the 80th anniversary of the first commercial FCC unit, which started up in Baton Rouge, Louisiana. So throughout that 80-year history, Grace has been proud to be the market leader globally in FCC catalysts, and I'm honored to be a part of such a great company. We're global. We're operating in over 30 countries, and we have customers in over 60 countries as well. We're number one in the technology areas listed here: FCC catalysts, hydroprocessing, hydrocracking, and also some other catalyst technologies and material technology segments as well, as listed on the slide. So in today's presentation, we'll start from a macro view, talk a little bit about the market, refining economics, refining outlook, and then drill down to FCC technology, and then ultimately to FCC catalysts and what catalysts can do to improve refining profitability. So consistent with the theme of some of the earlier talks, it's a great time to be in refining. Margins are strong. Global major products demand are very strong relative to prior years. Shown on this graph on the left side is a plot from some industry consultants, IHS Markit, about global products demand by region versus 2019 levels. And the lines at the top of this trend are from Asia. So Asia-Pacific region is leading the recovery and has contributed to the majority of the growth in recent years and expected to continue to do so in the coming years. Top right chart shows global average gasoline crack spreads, which are again above the 5-year average. The gray and red lines show 2022 and 2023, which are above the average. And so overall, a very bright future for our industry and very favorable margins. As a result, refiners are delaying maintenance. Global refinery turnarounds are expected to be at 5-year lows in the coming near future. And FCC margins have actually reached the highest levels in nearly a decade. And what are refiners doing in response to this unique high-margin environment? They're responding with implementing premium catalyst technologies, which we'll get into during this presentation. Okay, so drilling down a little bit further, keys to enhancing FCC profitability, it's really a three-pronged approach. And the first is hardware design. Hardware involves the steel on the ground, the licensor technology that's employed at your facility, the internals, and what those contribute to the overall operation. Then you have operating strategies. You know, what temperatures and pressures are you running? What feeds are you running? How you're operating the unit, and what constraints you're pushing up against. And then finally, catalyst solutions, which is where we'll spend the majority of today's talk. Catalyst solutions can have a major impact on overall max profitability of the operation when you put those all together. And just a plug about a presentation that some of our Grace colleagues gave at the American Fuel and Petrochemical Manufacturing Conference in the US, AFPM. They gave a talk about FCC unit health check. And with today's refining margins, you know, is your unit really ready to take advantage of these high margins, run at max throughput? I encourage you to check that out on our eCatalyst website, which is available to our Grace customers. Okay, drilling down a little bit further into FCC catalyst design. Overall, FCC catalyst design is a fairly complex subject. There's a diverse range of materials that can go in there, including the actual platform itself, the zeolite type, which can vary pretty broadly in terms of quality, in terms of acidity, in terms of stability, and overall yield profile. You have the processing to control the physical properties. You have metals tolerance, which we'll cover in this talk as well. that can really control how much of the unwanted products that your operation makes. Then you have your matrix, which controls quite a bit around the porosity, and also your clay, which gives you your particle integrity. So overall, pretty complicated mix of ingredients and processing components that go in there. But overall, it's a neat industry to be a part of, and it really allows us to have flexibility to optimize to a particular unit's desires and objectives. So within FCC catalysts, rare earth has a very important role. It is pretty well known in industry that increasing rare earth on zeolite increases the hydrogen transfer activity. It increases the unit cell size and also leads to lower LPG olefinicity. It manipulates your active site density and can give you a pretty broad range of catalyst properties, catalyst activities, and overall selectivities. This plot on the top right is the impact of unit cell size on hydrogen transfer. So on the y-axis, we have the ratio of isobutylene to isobutane, which is effectively your hydrogen transfer index, and that's cross-plotted against cell size, which tells you the well-known idea that with higher unit cell size, you have a little bit more hydrogen transfer, and with a lower unit cell size, you generate more LPG olefins, and your LPG stream is overall had a higher olefinicity. So now we talk about rare earth on zeolite already. Now we want to talk about the second role of rare earth in FCC catalysts, which is rare earth on matrix. Rare earth on matrix is very important because it can have a very pronounced impact on the yield selectivity profile without influencing the LPG olefinicity itself. It does not interact with the zeolite, it does not deteriorate LPG olefinicity as a result, and it can be very effective in improving coke and gas selectivity. Shown here on the bottom right are EPMA images from a refiner ECAT sample. We have rare earth on the left, and we have vanadium on the right. And you can see the association or hotspots based on the color density that shows the rare earth-based metals trap is very effective at trapping the vanadium in this commercial unit. So again, rare earth on matrix, separate from rare earth on zeolite, and two separate functions overall of rare earth on a catalyst. Okay, we talked a little bit about contaminant metals. In terms of contaminant metal tolerance, it's really dependent on a particular FCC unit as well as the catalyst technology that's employed. This graph has data from three different FCCUs, the FCCU1 in black, 2 in blue, and 3 in red. And you can see the cross-plot of activity versus contaminant metals, vanadium plus sodium. There's a pretty drastic difference in some of these trends, in some of these slopes. The black data points have a slope of about -3, so about 3 number activity loss for 1,000 ppm of vanadium plus sodium. The red one's about closer to 2.5, and then the blue is pretty drastic at over 7. So you can have a major effect on the metals tolerance and activity retention based on the catalyst properties and also the actual unit itself. Diving a little deeper into vanadium deactivation. So vanadium is a well-known contaminant in FCC, originates from the feed. Shown here is the mechanism by which it attacks the catalyst itself, transfers onto the catalyst particle surface, moves over to the regenerator where it is oxidized and eventually forms vanadic acid. And the vanadic acid catalyzes the destruction of the zeolite framework. And so the more effective a trap is at reducing the mobility and the harmfulness of the vanadium itself, the better the impact on the unit operation. We saw some data in the earlier slide, but as far as a rule of thumb, typically about 1,000 ppm vanadium plus sodium will result in about a 2.5 number activity loss at a given fresh catalyst addition rate. As far as vanadium trapping technologies, we covered the rare earth-based technology from Grace in pretty much quite a bit of detail. They're based either on rare earth or alkaline earth elements, such as magnesium and calcium. However, there's an important distinction between rare earth-based traps and alkaline earth metal-based traps. Mag and calcium can be deactivated and form compounds within a FCC unit. Mag oxide can react with SiO2 to form magnesium silicate or forsterite, and calcium can react with SOx to form calcium sulfate or anhydrite. So these are very common elements within the regenerator operation. They're very present, and they're more abundant than vanadium. So that's the drawback of utilizing a mag or calcium-based trap, because they can be readily poisoned and converted into a stable compound. Rare earth oxides have less affinity overall to the sulfate formation and forming compounds, and therefore commercially they've been demonstrated to have a very effective trapping functionality for vanadium. Okay, now we'll get into some more data. This next couple slides are from a DCR study, that's Davison Circulating Riser, where samples were tested at high metals loading, and just to compare the effectiveness of a rare earth-based metals trap. So on the left side we have catalyst 1, and on the right side we have catalyst 2 being high rare earth. The rest of the properties were about similar, but you have about a 3% difference in rare earth on catalyst. First plot here is cat to oil versus conversion. Again, black is the lower rare earth and green is the higher rare earth catalyst. Pretty much a layover, similar activity between the two catalysts that were tested here. And then to the point in comments made earlier, LPG olefins, you have your propylene and butylene, and you can see despite the higher rare earth on the catalyst 2, the propylene is arguably a slight smidgen higher, and butylene is about similar as well. So no major difference in LPG olefinicity, indicating that, again, the Grace rare earth-based metals trap does not affect hydrogen transfer activity, given the distinction between rare earth on zeolite and rare earth on matrix. However, you look at the coke and hydrogen, what we like to call coke and smoke, the unwanted products. With the high rare earth catalyst, you have a pretty nice reduction in coke and also a large reduction in hydrogen, given that the metals are being effectively trapped by the rare earth metals trap. So there's a clear benefit for the catalyst 2 in this operation, and as shown by the data that we just reviewed. Now moving on to a few commercial case studies. This was a refiner in EMEA region that moved to a catalyst that had a higher rare earth on catalyst. Looking at the top right, you can see the change out. They went a couple % increase in rare earth, and the theoretical change out is shown there as well based on the rare earth marker. And the objectives were to lower delta coke, which was demonstrated here, moving from the blue low rare earth grade to the green high rare earth grade. So a nice reduction in delta coke at a given conversion. Improved gas selectivity, so similar, maybe slightly lower gas selectivity at a given conversion level for this refiner. And then negligible change in overall LPG yield, but a nice boost in LPG olefinicity. So the objectives of this refiner were met. They wanted to boost LPG olefinicity with negligible change to LPG yield overall. So hence a reduction in LPG sats. Another case study, this was a reformulation to a higher rare earth catalyst, and they wanted to preserve the LPG olefin selectivity. So the base is in orange on this plot, and the high rare earth is in green. And the axes are ECAT ACE data. It's propylene over kinetic conversion on the y-axis, and ACE C3 and C4 on the x-axis. So again, a layover in data, and no remarkable difference was observed in terms of selectivities. So reinforcing the point about high rare earth technologies being favorable on LPG olefin make. So we looked at a lot of data. So to tie it all together, as far as the Grace integral vanadium trap technologies, we've got a couple images that compares and contrasts Grace technology versus that of a competitor. So a goal for a metals trap is to reduce coke and hydrogen make. That's the end goal. I want to reduce the harmful effects of contaminant metals and protect the zeolite from deactivation. Looking at the image on the left is the SEM mapping of key elements, silica in blue, lanthanum in purple, and mag in orange, magnesium. And you see pretty even dispersing of the elements through all the particles, integral, and it's very evenly interspersed. And then we contrast that with a competitor sample on the right, where you see high density separate components of silica, magnesium, and lanthanum, which carries its own disadvantages in that there can be preferential loss of a component especially with blends that use active components, metals trapped separate, and also inert particles. And you have to also depend on vanadium mobility for the trap to work, inter-particle mobility of the vanadium in order for the trapping technology to work. So some key differences that we wanted to highlight on this slide. For those that were present last year on the virtual GRPC 2021, we talked about our fusion technology, which is a novel catalyst platform, contains a high rare earth base, and it has demonstrated very wide commercial success in the industry, delivering coke selectivity advantages while preserving key yields on LPG olefins and gasoline. The Grace team will be happy to talk more about this. We also have our RIVE technology, which we've spoken about in prior conferences, and also a new technology, which we're not at liberty to say yet, but later this year we'll have a big unveiling. But we're constantly innovating at Grace. We're driving forward our technology, continuing to move the needle, and wanting to deliver value to refiners given the high margins and challenges that we all face today. So in summary, refining outlook and margins have been very strong. They've been strong in the recent months and also are forecasted to remain strong in the coming years. Our refiners overall are processing very high rates and utilizing premium catalyst technologies to deliver value in those operations. There are several factors that are involved in maximizing FCC profitability, with catalyst design as the forefront of that. Grace, as I mentioned, is constantly innovating. We've got novel catalyst technologies, including fusion and also RIVE, that employ a high rare earth-based metals trap that offers key advantages such as coke and gas selectivity, and all while not affecting hydrogen transfer activity. And it has integral particles to prevent selective losses as compared to alternative technologies. So with that, I hope I compelled you to keep an open mind, and I invite you to keep an open mind about rare earth on catalysts, because rare earth specification limitations can really constrain optimal catalyst selection. There's certainly a balance, right? Rare earth on zeolite is important, rare earth on matrix is important to really deliver that balance and to push an FCC unit to multiple constraints, which is the end game. And overall, refiners with high propylene targets will not see an impact on propylene selectivity using Grace rare earth-based metals traps. And we went through several examples. And again, catalyst technology is an interesting industry and allows for optimization of the FCC to multiple constraints. And hope that was interesting. Thank you for your time and attention, and appreciate it. Thank you.
Thank you, Ken. Thank you very much. FCC catalyst evaluation selection is definitely a interesting and most challenging activity for any refiner, though the same activity is done every year or once in 2 years. He has brought out how the good effects of high rare earth are best utilized by overcoming some of its shortcomings. Thank you very much for it.